Good evening, and welcome to Cozy Sleep Time. Before we begin tonight's story, take a quiet moment to settle in and get comfortable. Find a position where your body can fully relax, whether you're lying in bed, resting on a couch, or simply unwinding after a long day. Allow your shoulders to soften. Let your breathing slow down just a little. There is nowhere else you need to be, and nothing else you need to do. Here on Cozy Sleep Time, we explore calm and gentle topics, stories designed to help the mind slow down and drift peacefully toward rest. Each story moves slowly, gently, allowing your thoughts to wander and your body to relax more and more. Our story tonight is about the wisdom of snow predictors. As the story unfolds, you can simply listen, or you can allow your mind to drift. There is no need to stay focused. If your thoughts wander, that is perfectly natural. So take one more slow breath, get comfortable, and let the quiet story begin. Clouds are the visible expression of atmospheric processes that shape our weather. Learning to read them is like learning a language that the sky writes every day. Cloud watchers through centuries developed classification systems that organize these fleeting formations into predictable patterns, allowing us to anticipate coming weather with remarkable accuracy. The foundation of modern cloud classification was established by Luke Howard in 1803. He proposed three basic categories based on shape: cirrus for wispy hair-like clouds, cumulus for heap-like piled clouds, and stratus for layered sheet-like clouds. His system recognized that while clouds appear infinite in their variety, they fall into recognizable types that convey specific information about atmospheric conditions. Howard's insight was recognizing that clouds, despite their endless variation, could be organized into categories as Linnaeus had organized living organisms. The International Cloud Classification builds on Howard's foundation with more detailed categories and altitudes. High clouds above 20,000 feet carry the prefix cirro, middle clouds between 6,500 and 20,000 feet carry alto, and low clouds below 6,500 feet carry no prefix. The suffix nimbus indicates clouds that produce precipitation, while Castellanus describes clouds with tower-like projections that suggest developing instability. Cirrus clouds are the highest and most ethereal, appearing as delicate white wisps or curls, often called mare's tail clouds. Composed entirely of ice crystals, because temperatures at their altitude fall far below freezing, cirrus clouds form when the upper atmosphere is sufficiently moist and turbulent to condense water vapor directly into ice. Their streaks show the direction of high-altitude winds, information vital for understanding weather patterns at the heights where jet streams flow. The presence of cirrus clouds often precedes changing weather. When cirrus thicken and lower over several hours, they signal that a warm front is approaching. The ice crystals that compose them are the first evidence of moisture moving in aloft, the visible signature of weather systems many hours away. This predictive value has been recognized for centuries, encoded in the saying that mare's tails signal coming rain. Cirrocumulus clouds appear as small white ripples or grains arranged in patterns, sometimes called mackerel sky for their resemblance to fish scales. They form when air rises and cools at altitude, producing cellular convection patterns that create the distinctive rippled appearance. These clouds typically indicate instability in the upper atmosphere and may precede thunderstorms within 24 hours. Their presence tells skywatchers to watch for developing conditions. Altocumulus clouds appear as white or gray patches in a patchy pattern at middle altitudes between 6,500 and 20,000 feet. They often form in rows or waves, revealing the pattern of atmospheric waves invisible to the naked eye. When altocumulus appear on a warm, humid morning, they often signal afternoon thunderstorms as the atmosphere continues destabilizing through the day. Cumulus clouds are the familiar puffy fair-weather clouds with flat bases and rounded tops. They form when morning sun heats the ground, causing air to rise and cool until it reaches the condensation level where water vapor transforms to visible droplets. Their flat base marks this condensation level precisely, showing the altitude where rising air first cooled to the dew point temperature. Fair-weather cumulus often appear in the late morning and dissipate by evening as the ground cools and rising air currents weaken. They indicate a stable atmosphere with moderate upward motion and no immediate weather concerns. Watching cumulus form in late morning and then fade in evening reveals the daily cycle of solar heating and convective activity that characterizes stable weather patterns in summer. Cumulonimbus clouds are the giants of the cloud world, reaching from near the ground to the tropopause at 40,000 feet or more in tropical regions. Their distinctive anvil-shaped tops spread horizontally, where the cloud encounters the stable air of the stratosphere, unable to rise further. These are the thunderstorm clouds, producing heavy rain, lightning, hail, and sometimes tornadoes. Their vertical extent indicates extreme atmospheric instability, conditions where warm, moist air rises rapidly. The formation of a cumulonimbus cloud requires three conditions working together. First, moisture must be abundant near the surface to provide the raw material for cloud droplets. Second, an unstable atmosphere must allow rising air to continue ascending rapidly. Third, some lifting mechanism, whether heating, a frontal boundary, or terrain, must initiate the upward motion. When all three align, thunderstorms develop. Towering cumulus, also called cumulus congestus, represent an intermediate stage between fair-weather cumulus and the full cumulonimbus. These clouds show significant vertical development but lack the anvil of a mature thunderstorm. They indicate that the atmosphere is becoming unstable and that thunderstorms may develop if conditions persist. The transition from cumulus to cumulonimbus can occur rapidly, sometimes in less than an hour. Understanding cloud formation requires understanding the journey of water through the atmosphere. This invisible journey begins when water evaporates from oceans, lakes, rivers, and plants, transforming from liquid to vapor that rises and mixes with the atmosphere. The details of this journey determine what kind of cloud eventually forms. Evaporation is the transformation of liquid water into invisible water vapor, requiring heat energy that the process absorbs from the surrounding air. This is why evaporation cools surfaces. The heat that disappears from the surface accompanies the water vapor as it rises. The moisture capacity of air increases dramatically with temperature, with warm air capable of holding far more water vapor than cold air ever could. A measure called relative humidity expresses how much water vapor air contains as a percentage of the maximum it could hold at that temperature. When relative humidity reaches 100%, the air is saturated and condensation can begin. However, saturation is not fixed at 100%. It varies with temperature, with higher temperatures possible before reaching saturation at any relative humidity value. This fact is central to understanding cloud formation. Condensation occurs when air temperature drops to the dew point, the temperature at which air becomes saturated and water vapor can transform to droplets. The dew point is not constant, but depends on how much water vapor the air contains. More humid air has a higher dew point, reaching saturation at higher temperatures. When the temperature drops to match the dew point through cooling, clouds form. The process of condensation requires surfaces on which water molecules can accumulate, called condensation nuclei. These tiny particles include dust, salt, pollution, and even microscopic organisms that provide the microscopic surfaces necessary for droplet formation. Without these particles, air can become supersaturated without forming clouds, creating the unusual phenomenon of cloud-free rain that has occasionally been observed when unusual atmospheric conditions coincide. Cloud droplets are remarkably small, typically 10 to 20 micrometers in diameter, small enough that millions occupy the space that a single raindrop would fill. A typical cloud contains hundreds of droplets per cubic centimeter, with each droplet forming around a single condensation nucleus. The enormous number of these tiny droplets explains why clouds appear white rather than transparent. Light scatters repeatedly as it passes through this field of droplets, bouncing between them in all directions. When air rises through the atmosphere, it encounters decreasing pressure that causes it to expand. This expansion produces cooling called adiabatic cooling, occurring at about 10 degrees Celsius per kilometer in unsaturated air. This predictable cooling explains why clouds form at specific altitudes where rising air first reaches the condensation temperature. Once air reaches the condensation level and cloud droplets begin forming, the process changes. Latent heat released during condensation, the same heat that evaporation absorbed, now warms the rising air. This slows the cooling rate to about 5 degrees per kilometer, half the rate of unsaturated air. This change produces the distinctive flat base that marks where rising air first produces visible cloud, a flattening that reveals the condensation level. Clouds form in several distinct ways, each producing characteristic cloud types. Frontal lifting occurs when different air masses meet, with warm air rising over cold air along a front. This lifting produces the extensive layered clouds characteristic of warm fronts and the towering clouds of cold fronts. Convective lifting occurs when the ground heats air, creating the cumulus clouds of summer afternoons. Orographic lifting occurs when air rises over terrain, creating clouds on mountain slopes. Frontal clouds develop along boundaries between different air masses. Warm fronts feature extensive stratus clouds formed by gentle, widespread lifting of moist air over the retreating cold air. Cold fronts feature steep lifting that creates cumulonimbus clouds and severe weather. These frontal cloud patterns provide the most reliable long-range weather predictions available. Convective clouds form when differential heating between surface and atmosphere creates unstable conditions. The ground heats unevenly during sunny days, creating columns of rising air. The cumulus clouds that form above these rising columns mark the columns of rising air, their bases showing the condensation level, and their tops revealing the altitude where rising air becomes cooler than the surrounding atmosphere. Summer afternoon thunderstorms often follow this pattern. Mountain-related clouds form when air rises over terrain called orographic lift. The distinctive lenticular clouds that form over mountain peaks, sometimes mistaken for UFOs, form in the standing waves that develop downwind of mountains. These clouds form and dissipate in the same location as air flows through the wave pattern, providing clues about wind patterns at altitude. Clouds can also form through mixing when two masses of air with different temperatures come together. The mixing can produce cooling if one mass is cooler than the saturation point of the resulting mixture. This process occurs along coastlines where warm, moist air meets cooler water, producing sea fog that is actually cloud forming at ground level as the mixing produces saturation. Snow represents one of the most beautiful and complex phenomena in meteorology. Unlike rain that simply falls from clouds, snow forms through intricate processes in cold atmospheres, building the intricate patterns that make each snowflake unique. Understanding snow formation reveals why some winter storms deliver light powder while others bring heavy wet snow that packs poorly. Snow forms in clouds where temperatures throughout the entire cloud layer fall well below freezing. Unlike the rain that falls from warmer clouds, snow crystals develop slowly in cold cloud environments, building their intricate structures molecule by molecule. The journey from cloud droplet to snowflake involves dozens of steps, each influencing the final crystal structure that reaches the ground. Ice crystal formation requires temperatures below -40 degrees Celsius, where spontaneous freezing can occur without external nuclei. At temperatures warmer than this threshold, water can remain liquid well below freezing, the remarkable phenomenon of supercooling that occurs in many winter clouds. Cloud droplets that remain liquid at temperatures as low as -40 degrees are common in winter storms, waiting for some trigger to begin freezing. The transformation from supercooled droplets to ice crystals produces the spectacular ice crystal formations that make snow unique. When supercooled droplets contact ice nuclei, they freeze almost instantly, releasing latent heat that helps the crystal continue growing. This released heat warms surrounding supercooled droplets, allowing them to also freeze in a chain reaction called the Bergeron-Findeisen process that spreads crystallization through the cloud. The growth of ice crystals proceeds through sublimation, where water molecules move directly from vapor to solid without becoming liquid. This direct vapor-to-solid transition produces the extraordinary crystalline patterns that characterize snow. The crystals grow asymmetrically, adding molecules preferentially at corners and edges where the molecular structure offers the most favorable attachment sites. Snow crystals grow as six-pointed stellar dendrites, the classic snowflake shape that appears on winter decorations. The specific pattern depends on the temperature and humidity conditions that the crystal experiences as it falls. Crystals grown at -2 degrees Celsius form thin plates. Those at -5 degrees form hollow columns. Those at -15 degrees form the elaborate stellar dendrites that most people recognize as snowflakes. No two snow crystals are identical, even though they all share the underlying hexagonal symmetry determined by the crystal structure of ice. The unique path each crystal takes through the variable temperature and humidity environment of a cloud produces unique growth histories. Despite billions of snow crystals examined by scientists over more than a century, no two have ever been found to match exactly. The classification of snow types provides important information for winter activities and forecasting. Powder snow consists of small, light crystals that pack loosely, providing the light, fluffy snow that skiers love. Packed snow consists of larger crystals that have been partially broken during fall, packing more densely and providing better snow for building snow structures. Corn snow consists of larger, wetter crystals typical of spring conditions. Lake effect snow demonstrates the relationship between open water and heavy snowfall. When cold air passes over relatively warm water, it picks up moisture that subsequently falls as heavy snow as the air rises over land. The Great Lakes produce enormous amounts of lake effect snow, with some locations receiving hundreds of centimeters annually. The crystals in lake effect snow tend to be smaller and lighter because they form quickly. The prediction of snow type requires understanding both the temperature profile through the cloud layer and the trajectory that crystals follow on their descent. Temperatures near freezing at the surface produce wet snow that packs and sticks. Temperatures far below freezing produce dry powder. The depth of the warm layer determines whether snow reaches the ground or melts and refreezes as ice. Snow forecasting combines understanding of cloud dynamics with the thermodynamic properties of water. Numerical weather prediction models simulate the complex processes within clouds to estimate snow accumulations. These models have improved dramatically in recent decades, though snow remains among the more difficult precipitation types to forecast precisely because small changes in temperature can produce large changes in accumulated snow. The observation of snow crystals themselves provides information about the conditions within clouds where they formed. Large stellar dendrites indicate that the cloud contains substantial moisture at moderate temperatures. Small columns indicate cold, dry conditions. Rimmed crystals indicate that the crystal passed through supercooled droplets. Professional snow observers catalog these crystal types to understand conditions aloft that could not otherwise be observed. Weather lore represents accumulated observations passed from generation to generation, the practical wisdom of people who depended on anticipating changing conditions without the benefit of modern forecasting. The scientific study of clouds provides a modern foundation for what traditional observers understood through careful attention to sky conditions. Both approaches offer valuable tools for anticipating precipitation, though modern science provides greater precision. Red sky at morning occurs when morning light reflects off clouds in the western sky, indicating weather systems approaching from that direction. In the mid-latitudes where most of North America and Europe lie, weather systems generally move from west to east. The morning sun, shining from the east, illuminates clouds associated with approaching weather in the west, producing the red glow. This signal has warned sailors and farmers of approaching storms for millennia. Red sky at night reflects the setting sun in the eastern sky, indicating weather systems that have passed to the east, moving away from the observer. The departing weather system reflects the departing light, giving the red glow that sailors and farmers have long associated with fair weather ahead. This ancient wisdom recognized the predictable movement of weather systems. Mare's tails, the traditional name for cirrus clouds, predict approaching weather systems within 24 to 48 hours. These delicate ice crystal clouds form in advance of warm fronts, where moist air meets cold air at altitude. The moisture that produces cirrus eventually spreads and lowers as the front approaches, bringing the precipitation that the initial cirrus warned of. The saying, "Mare's tails make loft ships carry sails," encoded this observation in maritime culture. The mackerel sky of cirrocumulus often precedes thunderstorms. These small ripples at high altitude indicate atmospheric instability that may develop into convective storms as the day progresses. While not always a reliable predictor in isolation, their presence combined with other observations signals that conditions may be favorable for storm development and should be watched. Halo phenomena around the sun or moon predict coming weather. The rings are produced by ice crystals in cirrostratus clouds that precede warm fronts. The larger the halo, the higher the ice crystals producing it. These halos are among the oldest documented weather observations, with records from China more than 2,000 years ago. They consistently predict precipitation within 12 to 24 hours. Ring around the sun or moon predicts rain within a day, as the same cirrostratus clouds that produce halos often herald approaching weather systems. This traditional saying has been validated by modern understanding of cloud sequences. Ground fog often burns off on sunny mornings in fair weather, but evening fog indicates high humidity and potential for dew or frost. Fog forms when radiative cooling brings surface temperature below the dew point and typically clears by midday as the sun heats the ground. This pattern indicates stable conditions with high moisture, potentially indicating approaching weather if fog forms unusually early or late. Traditional weather predictions extended beyond clouds to include animal and plant observations. Cattle gathering under trees before rain signals the drop in atmospheric pressure that often precedes storms. The reduced pressure is uncomfortable for animals that evolved seeking stable conditions. Birds flying lower before rain seek the shelter of trees and lower altitudes, behaviors that have physiological explanations but work as practical predictors. The behavior of birds has been studied scientifically for weather prediction. Some birds change their migration patterns in response to barometric pressure, with lower pressure triggering earlier departures. Their flights at different altitudes also indicate pressure patterns that influence weather forecasts. The behavior of insects provides shorter-term predictions than most animal signs. Bees working more industrially before rain, spiders appearing more prominently, ants appearing in unusual numbers, all provide potential short-term predictions. These observations can extend from minutes to hours and provide useful local indicators when combined with cloud observations. Natural signs have their limits. Climate change is altering the patterns that traditional observations encoded over centuries. Weather systems may now arrive from different directions or with different characteristics than the patterns that produced traditional observations. This increases the importance of combining traditional observation with formal forecasting. Modern forecasting methods incorporate cloud observations from satellites that see patterns invisible to any ground observer, radar that detects precipitation within clouds, and automated instruments that measure conditions precisely throughout the atmosphere. These tools provide far more precise predictions than traditional methods could ever achieve. Yet cloud watching remains valuable, providing information about conditions specific to local observations that global forecasts cannot capture. Forests might seem fundamentally different from the open sky where clouds form, yet forests are intimately connected with cloud formation and precipitation. The relationship works in both directions. Weather determines what kinds of forests can grow in different regions, while forests in turn influence the weather patterns that bring them moisture. Understanding these connections reveals one of the most important relationships between land and atmosphere. Forests release enormous amounts of water vapor through transpiration, the process by which plant roots absorb water from the soil and it escapes through small pores called stomata in the leaves. A single large tree may transpire hundreds of liters of water on a warm day. An entire forest can release moisture comparable to a small river, adding significant humidity to the atmosphere that can influence local and regional weather patterns. This forest-released moisture increases atmospheric humidity locally and downwind. Air flowing over tropical rainforests picks up moisture that later falls as precipitation as the air rises and cools. Deforestation reduces this source of atmospheric moisture, potentially reducing rainfall in downwind regions. The Amazon rainforest generates significant rainfall not only for Brazil but for surrounding countries, demonstrating the influence that forest transpiration has on regional precipitation. Cloud forests represent the most direct connection between forests and clouds. On windward mountain slopes where moist air rises and cools, clouds form at remarkably low altitudes, dripping nearly continuously on the forest below. The vegetation in these locations evolved to handle nearly continuous moisture, creating ecosystems found nowhere else on Earth. These cloud forests can receive more water from cloud drip than from conventional rainfall. The condensation level in mountainous regions often coincides exactly with the elevation where clouds form. This creates the striking visual of clouds streaming across ridge tops like waterfalls in the sky. These orographic clouds form as moist air is forced upward by terrain, cooling until it reaches saturation and condensation begins. The cloud base reveals exactly where the air temperature equals the dew point. Fog drip represents a passive form of precipitation unique to cloud forests. Cloud droplets that form on forest leaves grow heavy enough to drip onto the ground below, providing significant water input even without rainfall. Some cloud forests receive more water from fog drip than from conventional precipitation events, demonstrating how important this passive water capture can be. The relationship between forests and clouds is affected by forest clearing. Reduced transpiration after deforestation means less atmospheric moisture, potentially reducing cloud formation and rainfall both locally and downwind. In some regions, the connection between deforestation and reduced rainfall has been measured and documented, providing additional incentive for forest conservation beyond the value of the forests themselves. Traditional cultures often recognize these connections and managed forests to preserve them. Sustainable forest management often preserved the relationship between forests and precipitation that communities depended upon. Modern research validates these observations, quantifying the moisture cycling that connects forests and weather in terms that allow precise understanding. The value of forest transpiration goes far beyond the local effects. Forests release moisture that affects precipitation across entire regions. Protecting existing forests and restoring degraded ones provides benefits that extend far beyond the forest itself, including more stable precipitation patterns and reduced risk of drought. Weather prediction has been transformed by satellite technology that views the entire planet continuously. Weather satellites orbit the Earth, continuously photographing cloud patterns that reveal atmospheric processes invisible from the ground. The view from space shows the larger patterns that individual cloud observers cannot see, revolutionized forecasting that now extends days into the future with increasing accuracy. Geostationary satellites orbit at the same speed that Earth rotates, appearing fixed above a particular longitude at an altitude of about 35,800 kilometers. These satellites monitor the same region continuously, tracking the development and movement of weather systems that might be missed between ground-based observations. They provide the continuous watching that makes modern weather forecasting possible. Polar orbiting satellites circle the Earth from pole to pole, passing over each location twice daily at an altitude around 800 kilometers. These satellites carry instruments that measure temperature, humidity, and other variables throughout the atmosphere. They contribute the vertical profiles of atmospheric conditions that numerical weather prediction requires. The first weather satellite, TIROS-1, launched in 1960, demonstrated the potential for cloud monitoring from space. The television pictures of cloud patterns revealed the true extent of weather systems and began the transformation of meteorology that continues today. Modern satellites offer resolution and capabilities that would have seemed miraculous in those early days of space photography. Cloud imagery from satellites reveals patterns invisible from the ground. The spiral structure of mid-latitude cyclones, the circular organization of hurricanes, the streaming cloud streets over oceans all become visible from space. These patterns help meteorologists understand and forecast weather systems that might otherwise surprise communities. Infrared imagery detects the temperature of cloud tops, revealing their altitude and indicating storm intensity. Cold cloud tops indicate high, cold cloud tops characteristic of vigorous convection that can produce severe weather. This capability allows forecasters to identify developing thunderstorms well before they produce damaging weather. Satellite precipitation estimation uses cloud characteristics to estimate rainfall. The brightness of clouds in certain wavelengths relates to the amount of ice and water they contain, which relates to precipitation intensity. This helps estimate rainfall in regions without ground-based radar coverage. Clouds viewed from satellites reveal patterns that link with traditional weather observations. The spiral arms of approaching weather systems visible from space often match what cloud watchers on the ground observe as clouds approach. The higher perspective complements ground-based observations without replacing them. Climate change is altering the patterns that cloud watchers have learned to interpret over centuries. Warmer temperatures change the type and distribution of clouds, modify precipitation patterns, and create new weather phenomena that traditional wisdom never anticipated. Understanding these changes is essential for continued weather prediction in a changing world. Warmer temperatures increase the atmosphere's capacity to hold moisture in an extremely predictable way. For every degree Celsius of warming, the atmosphere can hold about 7% more water vapor. This increased capacity means more moisture is available during precipitation events, even as the total number of rainy days may decrease in some regions. The result is more intense precipitation events that can overwhelm drainage systems. Cloud patterns are shifting as the climate changes in ways that affect traditional prediction methods. In some regions, clouds are forming at higher altitudes as warming increases the altitude at which temperatures reach freezing. These higher clouds trap more infrared radiation, creating additional warming that accelerates the climate cycle in a feedback that continues to change cloud patterns. Traditional weather prediction methods may become less reliable as climate changes. The patterns that produced predictable weather sequences in the past are shifting, and observations made decades ago may no longer apply in the same way. This increases reliance on scientific methods while reducing the utility of some historical lore. Extreme weather events are becoming more frequent and intense as climate change continues. Heat waves last longer and reach higher temperatures than historical patterns would have predicted. Heavy precipitation events produce more rainfall in shorter periods than drainage systems were designed to handle. These changes challenge forecasters and communities to adapt to new weather realities. Winter weather patterns are particularly affected by warming because the threshold between snow and rain is rising. Warmer air holds more moisture that can fall as snow or rain, but what falls as snow is decreasing in regions that once received consistent snowfall. Some traditional snowfall regions now receive more rain than snow. Arctic amplification, the faster warming of polar regions compared to the rest of the globe, is changing atmospheric patterns dramatically. The reduced temperature difference between the equator and poles weakens jet stream winds, producing weather patterns that stall longer over one location. This contributes to both extended droughts and extended wet periods. The wisdom of cloud watching remains valuable even as climate changes. Observing clouds and their changes still provides useful information about local weather conditions. The patterns may shift, but the fundamental relationship between cloud forms and atmospheric processes remains valid and useful. Clouds on other planets reveal universal atmospheric principles that connect the study of clouds to the broader universe. The processes that form clouds on Earth operate similarly on any planet with an atmosphere, providing insights that extend understanding beyond our own world, while demonstrating the principles that govern all cloud formation. Venus features perpetual cloud cover in its dense atmosphere. Though these clouds consist of sulfuric acid rather than water, the cloud layer sits at an altitude of 50 to 70 kilometers, with visibility limited to a few kilometers within the cloud layer itself. The clouds of Venus demonstrate that cloud formation is not unique to Earth, but is a universal atmospheric process. Jupiter features prominent cloud bands that reveal atmospheric circulation patterns across the planet. These clouds consist of ammonia ice, ammonium hydrosulfide, and water ice at different levels within the atmosphere. The distinct bands show different atmospheric conditions at different latitudes, features that are visible even through small telescopes. Saturn features a nearly featureless atmosphere, with occasional storm systems that appear and disappear. The hexagonal storm at the North Pole demonstrates the extraordinary atmospheric dynamics possible on gas giant planets. The simplicity of Saturn's visible features compared to Jupiter demonstrates how atmospheric composition and dynamics affect cloud formation. Mars features thin clouds that form in limited areas and seasons. Water ice clouds form in regions where temperature and pressure allow, while carbon dioxide clouds form near the poles in winter. The limited cloud cover is appropriate for the thin Martian atmosphere that contains only 1% of Earth's atmospheric pressure. Titan, Saturn's moon, features a dense atmosphere with surface pressure 50% greater than Earth's. Clouds of methane form and precipitate in a cycle that parallels Earth's water cycle in some ways, with methane playing the role that water plays on Earth. This demonstration of similar processes beyond Earth reveals the universal principles of cloud formation. The comparison of clouds across the solar system demonstrates that cloud formation is a fundamental atmospheric process. Any planet with sufficient atmospheric pressure and appropriate temperature conditions can produce clouds, regardless of what the cloud particles are made of. Understanding clouds on Earth provides the foundation for understanding clouds across the universe. Exoplanet studies increasingly use cloud properties to understand distant worlds. The presence or absence of clouds reveals atmospheric conditions on planets that are too distant to observe directly. Future observations may reveal cloud patterns on Earth-like exoplanets that will inform understanding of conditions on those distant worlds. Nimbostratus clouds are the steady producers of overcast days and continuous precipitation. Unlike the dramatic vertical development of cumulonimbus, nimbostratus form gently through the steady lifting of moist air over a frontal boundary. These thick gray layers obscure the sun entirely, producing the gloomy days of extended precipitation characteristic of winter in maritime climates. The vertical extent of nimbostratus exceeds several kilometers, sufficient to produce extended periods of precipitation. The steady nature of the lifting that creates them produces steady precipitation rather than the showery pattern of convective storms. This steadiness is characteristic of warm fronts, where warm air glides slowly up and over cold air along a gently sloping surface. Nimbostratus formation represents the common situation where moisture-laden air rises gradually over an extended region. The cloud that forms extends for hundreds of kilometers, producing precipitation over wide areas. This is why warm front precipitation is more uniform than the hit-or-miss pattern of summer thunderstorms. The precipitation from nimbostratus is typically steady and extended, but rarely extreme. Amounts typically accumulate gradually, allowing water management systems to handle the flow. Problems develop when the steady precipitation continues for extended periods or when frozen ground prevents infiltration. Stratus clouds represent the lowest cloud form, essentially fog that has lifted from the ground. They form when the temperature drops to match the dew point through gradual cooling, or when gentle lifting produces condensation. The featureless gray of stratus obscures higher terrain that might be visible in clearer conditions. The depth of stratus clouds determines the severity of the obstruction they cause. Thin stratus might produce only diffuse light, while thick stratus might produce near darkness. The difference in cloud base altitude, measured in hundreds of meters rather than thousands of feet, distinguishes stratus from higher cloud forms. Stratus clouds are particularly common along coastlines, where cold water keeps the air temperature near the dew point. The California coast, the Pacific Northwest coast, and coasts in similar latitudes experience extended stratus during summer when inland heat produces the temperature contrast that maintains stratus. This coastal stratus is one of the signature cloud types of Mediterranean climates. The dissipation of stratus provides important information about coming conditions. When morning fog or stratus lifts and clears, it often indicates that solar heating will overcome the moisture that produced the cloud. The timing of dissipation helps indicate the stability of the atmospheric boundary layer and likely conditions through the day. Morning sky observations provide critical information about coming weather that is lost in automated observations and remote sensing. The sky near sunrise is at low angles that satellites cannot see clearly, where the interaction of early light with clouds provides information about atmospheric conditions throughout the troposphere. Learning to read the morning sky transforms casual observation into meaningful prediction. Watching the eastern sky before sunrise reveals the approach and passage of weather systems in ways that daytime observation cannot match. The quality of light at solar angles of less than 10 degrees reveals details of cloud structure and moisture that are hidden at higher angles. The colors of sunrise indicate the cloud types in the eastern sky and their likely progression toward the observer. Red coloration in the morning sky typically indicates clouds in the west reflecting the light of the rising sun. Since weather systems in the middle latitudes typically move from west to east, red in the morning indicates weather that has already passed. The traditional saying about red sky at night reflects this understanding of weather system movement. The depth of red coloration provides information beyond the simple presence of clouds. Thin clouds produce less coloration and appear yellow or orange. Thick clouds produce more intense reds. The rapid transition from darkness to red sky indicates that the clouds are approaching rapidly. Slow transitions indicate slower movements. The vertical extent of clouds can be estimated from morning sky observations in ways that remote sensing does not easily provide. Clouds that light up from below show that they are at least partially transparent to sunlight. Clouds that remain dark even as surrounding areas light up are thick enough to block sunlight, indicating significant vertical extent. The direction of approaching weather systems influences morning sky observations. West to east movement in mid-latitudes creates the pattern of morning eastern sky reflecting weather to the west. Southern or northern movements create different patterns that require different interpretations. These variations require understanding local circulation patterns. Morning fog patterns provide information about coming days that complement cloud observations. Fog that clears slowly indicates high humidity that may produce afternoon clouds. Fog that clears quickly indicates dry conditions that typically persist. The timing of fog dissipation relates to the balance of moisture and heating that will persist. The presence of contrails in the morning sky indicates the humidity at altitude that might eventually produce natural clouds. The persistence or disappearance of contrails through the morning reveals whether conditions at altitude are becoming more or less favorable for cloud formation. The connection between contrails and natural cloud formation demonstrates the relationship between human activities and natural cloud systems. Radar revolutionized precipitation forecasting by detecting the actual presence of precipitation within clouds. The ability to see inside clouds reveals where precipitation is falling and how intense it is, providing information that cloud observation alone cannot provide. The combination of radar with cloud observation provides the most complete understanding of precipitation. Weather radar works by sending pulses of microwave energy into the atmosphere and measuring the energy reflected back. Larger precipitation particles reflect more energy, allowing the radar to estimate precipitation intensity. The movement of precipitation toward or away from the radar produces the Doppler shift that reveals wind speed and direction within storms. Radar reflectivity is measured in decibels relative to a standard particle, usually expressed as dBz. Light precipitation returns signals around 20 dBz. Heavy precipitation returns signals above 50 dBz. The intensity colors on radar images from green through yellow to red indicate increasing precipitation intensity. Doppler radar can detect rotation within storms that might produce tornadoes. The characteristic velocity patterns that indicate rotation allow warnings that give people in the path of tornadoes minutes to seek shelter. This capability has saved countless lives since Doppler radar became operational. Radar has limitations that require understanding to interpret properly. Ground clutter can produce false echoes near the radar. Anomalous propagation can create echoes that do not represent precipitation. The radar beam spreads as it travels, decreasing resolution at longer ranges. These limitations require combining radar with other observations. The radar beam rises above the ground as it travels because of Earth curvature. Distant storms may be missed entirely if the beam passes above them. The lowest elevation scan may miss precipitation in the lowest kilometers of the atmosphere where significant weather may occur. Radar observations of winter precipitation present particular challenges. Snow produces weaker radar echoes than rain for the same precipitation rate. The radar often underestimates snowfall intensity, particularly in light snow events. Combining radar with other observations is especially important for winter weather forecasting. Dual polarization radar sends both horizontally and vertically polarized pulses, receiving information about the shape of precipitation particles. This allows distinction between rain, snow, and mixed precipitation. It also reveals the presence of debris in tornadoes, confirming tornado occurrence even when the tornado is not visible. Combining radar observations with cloud observations produces the most complete picture of precipitation systems. Radar shows where precipitation is falling and its intensity. Cloud observation shows why precipitation is falling and what can be expected as the system evolves. The combination of the two observation types enables the most accurate forecasts. The scientific study of clouds has progressed far beyond simple classification into a sophisticated understanding of cloud physics and cloud-climate interactions. Modern cloud physics addresses questions that range from the fundamental processes of cloud formation to the role of clouds in climate change. This understanding informs both weather prediction and climate forecasting. Cloud microphysics examines the small-scale processes within clouds that determine cloud behavior. The nucleation of cloud droplets, the growth of droplets into precipitation, the formation of ice crystals, and the interactions between droplets and ice crystals all fall within cloud microphysics. Understanding these processes allows more accurate prediction of cloud behavior. Cloud-aerosol interactions examine the relationship between atmospheric particles and cloud formation. Aerosol particles serve as cloud condensation nuclei, the surfaces on which water vapor condenses to form droplets. More aerosols produce more droplets, but smaller droplets, affecting both cloud reflectance and precipitation processes. Cloud-aerosol interactions reveal why clouds may not respond to climate change in simple ways. Increased aerosols from pollution might prevent the expected cloud brightening that simple theory would predict. Understanding these interactions is crucial for predicting how clouds will affect climate change. Cloud radiative effects determine how clouds affect Earth's energy budget. Low clouds reflect sunlight and cool Earth's surface. High clouds trap infrared radiation and warm Earth's surface. The balance between these opposing effects determines whether individual clouds warm or cool the climate system. Cloud feedback is one of the largest uncertainties in climate prediction. The ways that clouds might change in response to warming remain poorly understood, despite decades of research. Different climate models produce very different cloud responses, producing the largest spread in climate predictions. Cloud seeding represents an attempt to modify cloud precipitation. Silver iodide particles serve as ice nuclei that can initiate ice crystal formation in supercooled clouds. The effectiveness of cloud seeding remains controversial, with some experiments reporting increased precipitation and others showing no effect. The study of clouds extends to other planets and exoplanets. The principles learned from Earth clouds inform our understanding of planetary atmospheres throughout the solar system and beyond. This comparison reveals which cloud behaviors are universal and which are unique to Earth conditions. Clouds serve as indicators of atmospheric conditions across scales from local to global. Observing clouds provides information about temperature, moisture, wind, and stability. This information supports forecasts from hours to decades, depending on the scale of observation and analysis. Photography has transformed cloud watching into both science and art. Cloud photographers capture the fleeting beauty of atmospheric conditions that otherwise last only moments. The study of cloud photographs has helped meteorologists understand cloud development, while the appreciation of cloud beauty has inspired generations of sky watchers. Time-lapse cloud photography reveals atmospheric dynamics that the human eye cannot perceive. Clouds moving at speeds the eye cannot follow become visible as they flow across the sky. The development of individual clouds becomes visible over seconds that mark the transition from cumulus to cumulonimbus. This capability reveals information about atmospheric processes. Cloud photography has a long history of scientific contribution. Early photographs documenting cloud types helped refine classification systems. Time-lapse sequences document the life cycles of different cloud types. The study of these sequences has contributed to understanding of cloud dynamics that continue today. Cloud photography extends to satellite imagery that documents the global view. These images reveal patterns from individual clouds to global circulation that inform the understanding of atmospheric processes across all scales. The combination of ground-based and satellite cloud imagery provides complete coverage that neither could achieve alone. The art of cloud photography combines technical skill with patience and knowledge. Knowing when clouds will appear and how they will develop helps position the photographer for the best composition. Understanding cloud types helps anticipate the forms clouds will take. The best cloud photographs combine scientific knowledge with artistic vision. Cloud photography serves science by documenting phenomena that might otherwise be missed. The appearance of unusual cloud forms, the development of storm systems, and the sequence of clouds preceding weather changes can all be captured for later analysis. These records extend observation far beyond what any single observer could achieve. The appreciation of cloud beauty contributes to the protection of atmospheric conditions. People who value cloud beauty become advocates for clean air policies. The visual impact of beautiful clouds motivates conservation efforts that might otherwise seem abstract or distant. This aesthetic connection to the atmosphere contributes to environmental protection. Clouds inspire artists and scientists alike, connecting those who study them professionally with those who simply enjoy watching the sky. The shared appreciation of cloud beauty transcends the differences between professional and casual observers, creating community around the common experience of looking up at the ever-changing sky. Understanding why clouds rain requires understanding both cloud physics and precipitation processes. Clouds form when air rises enough to cool to the dew point, but clouds do not automatically produce precipitation. The additional processes that produce rain involve collisions, accumulation, and gravity in the complex dance between water and ice. Collision coalescence is the process by which cloud droplets collide and merge into larger drops. Cloud droplets form at sizes of 10 to 20 micrometers, too small to fall as rain. Larger droplets fall faster and collide with smaller droplets, growing rapidly through this coalescence. This process dominates in warm clouds where no ice is present. The Bergeron-Findeisen process operates in mixed-phase clouds with both supercooled droplets and ice crystals. Because ice saturation vapor pressure is lower than water saturation vapor pressure, ice crystals grow faster than surrounding droplets. They collect droplets that freeze on contact, growing rapidly into snow. This process can produce heavy precipitation from clouds that might otherwise be unable to do so. Riming occurs when ice crystals fall through supercooled droplets that freeze on contact with the crystal. Light riming produces snow. Heavy riming produces graupel. The density and shape of precipitation depends on the amount of riming. The appearance of rimed crystals helps identify the processes that produced the observed precipitation. The breakup of raindrops produces smaller droplets that can continue falling rather than joining larger drops. This breakup can cause additional precipitation below the cloud, as smaller drops produce the appearance of lighter precipitation continuing after the main drop passage. The breakup process limits raindrop size and increases precipitation intensity. The prediction of precipitation type requires understanding the temperature profile from cloud to ground. Snow falls when all temperatures are below freezing, rain when some layers are above freezing, freezing rain when a warm layer is between freezing layers aloft and a cold layer at ground. The complexity of these profiles makes prediction difficult, particularly in transitional seasons. Mountain effects on precipitation demonstrate orographic enhancement. Air rising over mountains produces additional lifting and cooling, enhancing precipitation on the upslope side. This effect produces some of the heaviest precipitation on Earth in mountains like the Pacific Northwest and the Himalayas. Noctilucent clouds represent one of the most unusual cloud types, forming at extreme altitudes around 80 kilometers in the mesosphere. These highest clouds form only in summer at high latitudes, when the temperature drops enough for ice to form at these very high altitudes. Their occurrence indicates specific conditions in a layer of the atmosphere that is otherwise notoriously difficult to study. Polar stratospheric clouds form even higher, at altitudes around 20 to 25 kilometers in the winter polar stratosphere. These clouds play a crucial role in ozone depletion by providing surfaces where ozone-destroying reactions occur. Understanding these clouds helped understand the ozone hole and informed international responses to ozone depletion. The study of these rare cloud types contributes to understanding atmospheric processes in general. The conditions at these extreme altitudes affect conditions throughout the atmosphere. Understanding how clouds form in extreme conditions informs understanding of more common cloud types. Mountain wave clouds form in the standing waves that develop downwind of mountains when stable air crosses mountainous terrain. The lenticular clouds that form in these waves have distinctive saucer shapes that have been mistaken for UFOs. Their location reveals where the atmosphere is producing wave motion. The relationship between mountains and wave clouds demonstrates the connection between surface features and atmospheric behavior. Mountains create waves in the atmosphere much as waves ripple across water. The clouds that form in these waves reveal atmospheric processes that would otherwise be invisible. Morning glory clouds in Australia represent another spectacular wave phenomenon, forming in the morning ahead of sea breezes. These roll clouds can extend for hundreds of kilometers, carrying the morning air in an advancing roll that is visible as a rolling cloud on the horizon. These spectacular formations demonstrate atmospheric wave processes at their most visible. The rarest cloud types often receive the most attention because they reveal unusual conditions. Understanding why these clouds form requires understanding the specific conditions that produce them, and the investigation often reveals conditions in the atmosphere that might otherwise be missed. Cloud watching rewards attention with ever-changing variety. The sky never looks exactly the same way twice, providing infinite variety for observation. This variety ensures that cloud watching remains engaging even after decades of observation. Weather prediction through direct observation combines knowledge, patience, and attention to details that remote sensing cannot capture. The process of predicting weather from cloud observations requires understanding the atmosphere as a continuous system in which changes at one level influence conditions throughout. This integrated understanding developed over centuries of observation. The first step in direct prediction is systematic observation, noting cloud types, sequences, and changes. This systematic approach developed into formal observation protocols that professional meteorologists use today. The tradition of sky watching extends far back into human history. The second step is developing predictions from the observed patterns, requiring both understanding of atmospheric processes and knowledge from traditional sources. Combining these two knowledge sources produces predictions that are more reliable than either could produce alone. The third step involves verifying predictions and adjusting expectations when predictions fail. The continuous improvement of weather prediction skill requires this feedback loop. Each successful and unsuccessful prediction provides information that improves subsequent predictions. The value of direct observation includes the specificity of local information. Satellite images show large-scale patterns but miss local variations that direct observation captures. The observation of specific clouds in specific locations provides information that serves local decisions. The community dimension of weather observation contributes to both prediction and appreciation. Shared observations of approaching weather systems create community response that contributes to public safety. The shared appreciation of cloud beauty creates communities that value the atmospheric commons. The practice of weather observation connects individuals with the atmosphere in ways that automated measurements cannot. The attention to cloud forms and changes develops skills and sensitivities that contribute to understanding of environmental conditions. This connection to the atmosphere has value beyond prediction. The future of weather observation includes both traditional methods and modern technology. Automated instruments provide continuous monitoring that extends human observation. Remote sensing provides views that human observers cannot achieve. The integration of these capabilities produces the most complete understanding. The wisdom of cloud watching remains relevant even as technology advances. The integration of traditional observation with modern technology produces the most effective approach to understanding weather. This combination continues the tradition of sky watching that has been valuable throughout human history. The relationship between oceans and clouds forms one of the most important connections in Earth's climate system. The heat capacity of oceans stores enormous amounts of energy that drive atmospheric circulation. The moisture evaporated from ocean surfaces provides the water that forms clouds. This ocean-atmosphere connection determines weather patterns across the globe. Ocean surface temperatures determine atmospheric stability and convective potential. When ocean temperatures exceed certain thresholds, the atmospheric instability becomes sufficient for tropical cyclone formation. The warm waters of the tropical oceans provide the energy source for these powerful storms. The El Niño Southern Oscillation demonstrates how ocean temperatures affect global cloud and precipitation patterns. The warming of eastern Pacific waters shifts rainfall patterns across the Pacific Basin, causing droughts in some regions and floods in others. These shifts in cloud and precipitation patterns have global consequences. Ocean-atmosphere interactions extend to mid-latitudes, where ocean heat and moisture influence storm formation and intensity. The contrast between cold ocean currents and warm air produces the fog and low stratus characteristic of coastlines like California and Oregon. These clouds affect solar radiation and temperature in ways that influence local ecosystems. The biological pump connects ocean productivity to cloud formation through aerosol generation. Ocean phytoplankton produce dimethyl sulfide, which oxidizes to create cloud condensation nuclei. More productive oceans produce more aerosols, which produce more clouds, which reflect more sunlight and cool the ocean surface. This feedback helps regulate Earth's climate. The ocean's role in the water cycle connects directly to cloud formation. The water evaporated from oceans eventually precipitates, with about 90% falling back into oceans and 10% falling over land. This connection determines where clouds and precipitation concentrate globally. The observation of clouds over oceans provides information about conditions that land-based observation cannot capture. Ship-based observations of cloud types provide information about atmospheric moisture and stability over water. Satellite observations of ocean cloud patterns reveal global patterns that affect climate regulation. Atmospheric stability determines whether clouds will develop vertically or remain flattened in layers. Stable air resists vertical displacement, producing layered clouds when forced to rise. Unstable air responds to lifting by continuing to rise, producing towering clouds when conditions allow. Understanding stability helps predict what kinds of clouds will form. The lifted index measures atmospheric stability by comparing the actual temperature to the temperature that a rising air parcel would reach. Positive values indicate stable conditions. Negative values indicate instability. The more negative the value, the more active convection is likely to become. This simple measurement helps forecast convective potential. The convective available potential energy, called CAPE, quantifies the potential for convection by measuring the energy available to a rising air parcel. Higher CAPE values indicate a greater potential for strong updrafts and severe weather. Values above 1,000 joules per kilogram indicate significant convective potential. The convective inhibition, called CIN, measures the energy required to overcome stable layers before convection can begin. High CIN values indicate that significant lifting is required to initiate convection, such as from daytime heating or front passage. The combination of CAPE and SIN determines when and how convection will occur. Skew-T diagrams provide the most complete picture of atmospheric stability. These diagrams plot temperature and moisture profiles in ways that reveal stability, CAPE, CN, and the altitude where clouds will form. The skill in interpreting these diagrams separates expert forecasters from beginners. Stability changes throughout the day in response to solar heating. Morning profiles show stable conditions. Afternoon profiles show unstable conditions as ground heating creates convective potential. This diurnal stability change explains why most convective weather occurs in afternoon and evening. Stability also changes seasonally as the sun moves between hemispheres. Summer conditions produce the most unstable profiles when solar heating is strongest. Winter conditions often produce stable conditions that limit cloud development. The seasonal variation of stability determines when different cloud types are most common. Climate change is affecting atmospheric stability patterns. Warmer surface temperatures produce more potential instability. Warmer upper troposphere may reduce stability aloft. The net effect on convection remains uncertain, but changes in stability patterns have been documented. Fronts represent the boundaries between air masses with different temperature and moisture properties. These boundaries are where most significant weather occurs, including the clouds and precipitation that define different weather types. Understanding fronts helps predict the sequence of weather that will occur. Cold fronts occur when cold air advances, pushing warm air upward along a steep slope. The lifting produces cumulonimbus clouds and showery precipitation, sometimes severe. The passage of a cold front typically brings clearing, lower temperatures, and more unstable conditions. The cloud types and weather associated with cold fronts are among the most dramatic. Warm fronts occur when warm air advances over retreating cold air, producing gentle lifting over a broad area. The gentle, widespread lifting produces stratus and nimbostratus clouds with extended precipitation. Warm front precipitation is typically steadier and less intense than cold front precipitation, but can last for extended periods. Stationary fronts occur when neither air mass advances significantly, producing extended periods of cloudiness and precipitation. These fronts can persist for days, producing what seem like extended rainy periods. The movement of these fronts often determines the length of rainy seasons. The cloud sequence at approaching fronts tells the story of approaching weather. Cirrus arrives first, followed by cirrostratus, then altostratus, then stratus, and nimbostratus. Recognizing this sequence allows prediction of approaching weather long before precipitation arrives. Occluded fronts occur when cold fronts catch up with warm fronts, lifting the warm air between. These complex fronts often produce the most intense weather as multiple air masses interact. The occluded front cloud types combine elements of both cold and warm fronts. The science of fronts developed from the polar front theory of Norwegian meteorologists in the early 20th century. This theory organized weather patterns into recognizable sequences that could be predicted. The fundamental understanding of fronts remains a cornerstone of weather prediction. The movement of fronts determines the day-to-day weather in mid-latitudes. Predicting front movement is one of the most important aspects of weather prediction. Small errors in front position can produce large errors in predicted weather. Convection drives the most dramatic weather phenomena, from summer thunderstorms to tropical cyclones. This vertical motion transfers heat and moisture between the surface and atmosphere, driving the global circulation that distributes energy from equator to poles. Understanding convection is essential for understanding the most significant weather events. Thermals are the small-scale convection currents that carry heat from the surface to the atmosphere. These invisible columns of rising air can be detected by their effect on dust and debris, by birds soaring on the rising air, and by the cumulus clouds that mark their tops. Thermals are the smallest scale of convection in the atmosphere. Convective available potential energy represents the energy available to drive convection. When the surface is warm and moist and the upper atmosphere is cold, the available energy can be enormous. The release of this energy produces rapid vertical motion that creates cumulonimbus and severe weather. Convective inhibition represents the stable layer that must be overcome before convection can begin. When CN is high, strong lifting is required to initiate convection, such as strong heating, mechanical forcing from fronts, or terrain. When CN is low, convection begins easily with only moderate heating. The transition from individual convection to organized convection represents one of the most important processes in severe weather prediction. Individual cells can merge into organized systems that produce more intense and longer-lasting weather. The prediction of this transition is critical for severe weather forecasting. Mesoscale convective systems represent the largest organized convection, covering hundreds of kilometers and persisting for hours. These systems are common in the Great Plains of North America during summer, producing both flash floods and severe weather. Understanding these systems requires understanding both the large-scale environment and the smaller-scale dynamics. Convection in the tropics differs from mid-latitude convection because the lack of strong temperature gradients limits large-scale organization. The individual thunderstorms of the tropics often produce more rainfall than their mid-latitude counterparts, but as smaller, more frequent events. This convection drives the global atmospheric circulation through heat transfer. The prediction of convection remains one of the most challenging aspects of meteorology. The scales involved range from individual thermals a few hundred meters across to convective systems hundreds of kilometers across. This range of scales is difficult to represent in forecast models, producing uncertainty in convective prediction. Lightning represents one of the most dramatic and dangerous weather phenomena. The electrical discharge that produces thunder and brilliant flashes connects cloud regions with opposing charges and can strike far from the thunderstorm itself. Understanding lightning helps predict and prevent one of weather's most dangerous hazards. Lightning forms when electrical charges separate within clouds through processes that are not fully understood. The prevailing theory involves the collision of ice crystals and graupel, which transfer electrons during collisions. The separation of these charges creates the electrical potential that produces lightning. Cloud-to-ground lightning represents only a fraction of total lightning, perhaps 20 to 25%. Most lightning occurs within clouds, carrying charge between different regions. Cloud-to-ground lightning is important because of its danger to people and structures. Lightning advances in steps called stepping, creating the branched lightning channel that is visible. The steps are so fast that the human eye perceives a continuous channel. The channel heats to temperatures hotter than the surface of the sun, producing the brilliant flash. Thunder is produced by the rapid heating of the lightning channel, which causes the surrounding air to expand explosively. The sound travels outward, producing the thunder that can be heard for kilometers. The time between flash and thunder indicates the distance of the strike. The distance of lightning can be estimated by counting seconds between flash and thunder and dividing by 5, the speed of sound in kilometers per second. Distances of 10 kilometers or more indicate particularly dangerous conditions. Lightning protection utilizes the property that lightning seeks the shortest path to ground. Lightning rods provide a preferred path that carries the current safely to ground. Proper grounding and protection systems reduce lightning dangers. Lightning detection networks use magnetic direction finders and GPS timing to locate lightning strikes precisely. These networks provide the data for lightning awareness and warning systems that reduce lightning deaths. Atmospheric moisture determines cloud types, precipitation, and weather patterns. The invisible water vapor that fills the atmosphere becomes visible when it condenses into clouds or precipitates as rain or snow. Understanding moisture and its measurement helps predict when clouds and precipitation will occur. Relative humidity expresses how close the air is to saturation as a percentage. When relative humidity reaches 100%, the air is saturated and condensation can begin. Values below 100% mean that evaporation exceeds condensation and clouds cannot form in that air. The variation of relative humidity through the day drives the formation and dissipation of clouds. Dew point represents the temperature at which air would become saturated if cooled. Unlike relative humidity, dew point is an absolute measure of moisture content that does not change with temperature. Higher dew points indicate more moisture in the air. When the actual temperature drops to the dew point, fog or dew forms. Dew forms when surfaces cool through radiation at night, cooling the air in contact with them. When surface temperature drops to the dew point, water vapor transforms directly to droplets on surfaces. This is why dew forms most readily on clear nights when radiation cooling is strongest. Frost forms when surface temperatures drop below freezing before dew point is reached. The water vapor transforms directly to ice crystals without becoming liquid, a process called deposition. Frost requires temperatures below freezing and sufficiently humid air. Humidity affects human comfort in important ways. High humidity prevents efficient evaporative cooling, making warm temperatures feel warmer. Low humidity causes drying of skin and mucous membranes. These effects influence both comfort and health. The moisture content of the atmosphere changes dramatically with altitude. Most atmospheric moisture is concentrated in the lowest few kilometers. This concentration explains why most clouds form below about 10 kilometers and why the highest clouds are composed of ice rather than water droplets. Humidity measurement has evolved from simple hygroscopes to sophisticated instruments. The psychrometer, which uses wet and dry bulb temperatures, remains useful. Modern electronic sensors provide continuous automated measurement that integrates into weather stations. Air pressure variations drive winds and storms, affecting every aspect of weather. Unlike temperature and moisture that are directly sensed, pressure requires instruments for measurement. Understanding pressure helps predict weather changes that might otherwise seem to appear suddenly. The connection between pressure and weather has been recognized for centuries. Atmospheric pressure decreases with altitude, reflecting the decreasing mass of air above. At sea level, the atmosphere weighs enough to exert pressure of about 1,013 millibars, the standard pressure at sea level. Higher elevations have lower pressure. High-pressure systems feature air descending in their centers, which suppresses cloud formation. The descending air warms and dries, producing the clear skies that often associate with fair weather. The clockwise circulation around high pressure in the northern hemisphere brings air from higher latitudes. Low pressure systems feature rising air, which cools and can produce clouds and precipitation. The counterclockwise circulation around lows in the northern hemisphere brings air from lower latitudes. The rising air in low-pressure centers produces the clouds associated with storms. Pressure changes indicate approaching weather systems. Falling pressure typically indicates approaching low pressure and storms. Rising pressure typically indicates approaching high pressure and clearing. The rate of pressure change indicates how quickly weather will change. Isobars on weather maps connect points of equal pressure, revealing wind patterns. Where isobar spacing is close, pressure changes rapidly, producing strong winds. Where isobar spacing is wide, winds are lighter. This relationship helps predict wind from pressure maps. The jet stream represents the strongest pressure gradient in the atmosphere, at the boundary between cold polar air and warm tropical air. This fast-moving ribbon of air drives weather patterns across mid-latitudes. The position and strength of the jet stream determines where weather systems will form and move. Barometric pressure has been measured with mercury barometers for centuries. The connection between pressure and weather inspired the development of weather forecasting. The simple observation of rising or falling pressure provides useful information about coming weather. Winds distribute heat and moisture across the planet, creating the weather patterns that affect every location. From gentle breezes to violent storms, wind shapes the environment in ways both subtle and dramatic. Understanding wind helps predict weather and explains the patterns that characterize different regions. The Coriolis effect results from Earth's rotation, deflecting moving air to the right in the northern hemisphere. This deflection creates the characteristic rotation of weather systems and the patterns of global wind. Without Earth's rotation, winds would flow directly from high to low pressure. Trade winds blow from subtropical high pressure toward the equator, bringing relatively constant easterly winds to tropical latitudes. These winds have been used by sailors for centuries to cross oceans. The position and strength of trade winds varies seasonally with the position of the sun. Mid-latitude westerlies blow from west to east, driven by the temperature contrast between poles and equator. These winds bring weather systems from the Pacific to North America and from the Atlantic to Europe. The strength and position of the westerlies varies seasonally and with larger climate patterns. Monsoons reverse seasonally, blowing toward continents in summer when land heats more than ocean, and toward oceans in winter when land cools. The Indian monsoon brings vital rainfall to support hundreds of millions of people. The predictability of monsoons enables agriculture in regions where rainfall is otherwise limited. Local wind patterns result from local heating and cooling, producing predictable daily wind directions. Sea breezes blow from ocean to land during daylight when land heats faster. Land breezes reverse at night. Mountain and valley winds flow upslope during the day and downslope at night. The Beaufort scale quantifies wind speed from observations, developed by Admiral Sir Francis Beaufort in the early 19th century. The scale ranges from calm to hurricane force, describing conditions at each level. The scale allows wind estimation without instruments, useful when technology was limited. Wind measurement uses anemometers that measure wind speed and wind vanes that measure direction. Modern automated stations measure and record wind continuously, providing data for forecasting and climate analysis. These measurements complement visual observations that capture effects instruments might miss. Tropical meteorology differs from mid-latitude weather in fundamental ways. The lack of strong temperature gradients in the tropics limits the large-scale organization that characterizes extratropical weather. Instead, tropical weather is dominated by convection and waves that move through the tropics, producing the patterns of cloud and rain that define tropical climates. The intertropical convergence zone represents the band of clouds and precipitation near the equator, where trade winds from both hemispheres meet. This zone shifts north and south following the sun, producing wet and dry seasons in tropical locations. The position of the ITCZ determines where tropical rainfall concentrates. Tropical waves are disturbances that move westward through the tropics, typically producing cloud and precipitation as they pass. These waves can develop into tropical cyclones when conditions are favorable. The prediction of which waves will develop remains challenging. Tropical cyclones represent the most powerful weather phenomena on Earth, requiring warm ocean water and favorable upper-level conditions to form. These rotating systems can span hundreds of kilometers and produce devastating winds, storm surge, and rainfall. Understanding their formation and movement is crucial for protecting coastal populations. Hurricanes, typhoons, and cyclones are the same phenomenon with different regional names. They all form over warm tropical waters and rotate around a calm eye. The eye forms where descending air creates a region of clear skies and light winds surrounded by the intense eye wall. Tropical cyclone forecasting has improved dramatically over decades. Track forecasts now extend days in advance with reasonable accuracy. Intensity forecasts remain more challenging. The improvements in forecasting have reduced deaths dramatically despite increasing coastal populations. Climate change may affect tropical cyclones in ways that remain uncertain. Warmer ocean temperatures may increase intensity. Changes in atmospheric moisture may affect rainfall. Storm tracks may shift. Understanding these changes requires continued research. Tropical cloud types differ from those in mid-latitudes. Deep convection dominates, with towering cumulus and cumulonimbus producing most precipitation. The trade wind inversions suppress mid-level clouds, producing the distinctive vertical development of tropical convection. Radar and satellite have revolutionized weather forecasting, providing capabilities that transformed prediction accuracy. Radar detects precipitation within clouds, revealing storm structure and intensity. Satellite provides the global view of cloud patterns that reveal the large-scale organization of weather. These tools complement each other in ground-based observation. Weather radar sends microwave pulses into storms and measures the energy reflected back. The reflection, called reflectivity, indicates precipitation intensity. Doppler radar measures the motion of precipitation toward or away from the radar, revealing wind patterns within storms. These capabilities have transformed severe weather warnings. Radar reflectivity patterns reveal storm types and severity. Supercell thunderstorms have distinctive hook echoes indicating rotation. Squall lines show the line of thunderstorms that produce severe weather. The recognition of these patterns enables warnings that save lives. Radar limitations include ground clutter, beam spreading, and beam blockage. Ground clutter produces false echoes near the radar. The beam spreads as it travels, decreasing resolution at long range. Mountains can block the beam, creating gaps in coverage. Geostationary satellites provide continuous images of the same region, tracking cloud patterns through time. These images reveal the movement and development of weather systems. The visible, infrared, and water vapor channels provide different information about atmospheric conditions. Satellite water vapor images reveal moisture patterns throughout the troposphere. These images show atmospheric rivers that transport moisture from tropical oceans to mid-latitudes. They reveal the position of jet streams and the movement of weather systems. Polar orbiting satellites provide detailed information about atmospheric temperature and moisture profiles. These profiles are essential for numerical weather prediction. The data from polar orbiters improves forecast accuracy significantly. The integration of radar, satellite, and ground observations provides the most complete picture of weather conditions. Each source provides information the others cannot. The combination enables more accurate forecasts than any single source could provide. The seasons result from Earth's axial tilt, producing the annual variation in solar energy that shapes weather patterns. As the northern hemisphere tilts toward the sun, the atmosphere warms and seasons transition from winter through spring to summer. The corresponding changes in cloud and precipitation patterns reflect the changing energy input. Winter features the lowest sun angle and shortest days, producing the least atmospheric heating. The reduced energy input produces the characteristic winter weather patterns. Storm systems develop along boundaries between cold polar air and warmer subtropical air, producing the frequent winter storms of mid-latitudes. Spring features increasing solar energy that destabilizes the atmosphere as ground warms faster than the overlying air. This instability produces the convective storms that become more frequent as spring progresses. The transition from winter to summer patterns creates the variability that characterizes spring weather. Summer features the highest sun angle and longest days, producing maximum atmospheric heating. The warm, moist air of summer produces the afternoon thunderstorms characteristic of summer afternoons. The high sun produces the clear skies that can bring extreme heat. Fall features decreasing solar energy that stabilizes the atmosphere as ground cools. The reduced instability decreases convective storm frequency. The season brings the first frosts that signal approaching winter and the return of winter storm patterns. The transition seasons of spring and fall feature the most variable weather. Cold air from polar regions can push south as warm subtropical air pushes north. The clashes between air masses produce the variety that characterizes these seasons. The timing of transitions varies from year to year. Monsoon seasons represent an extreme seasonal shift in wind and precipitation patterns. The summer monsoon brings moisture from oceans onto land, producing the rainy season in tropical and subtropical regions. The winter monsoon brings dry continental air, producing dry seasons. Seasonal prediction attempts to forecast months in advance whether the coming season will be warmer, cooler, wetter, or drier than normal. These predictions use ocean temperatures and other large-scale patterns that vary slowly. Seasonal forecasts inform decisions in agriculture, water management, and emergency preparedness. Air quality and clouds are connected in ways that affect both climate and health. Atmospheric particles affect cloud formation, while clouds affect the transport and removal of pollutants. Understanding these connections helps address air quality problems while accounting for the effects of pollution on climate. Aerosols are tiny particles suspended in the atmosphere that serve as condensation nuclei for cloud droplets. More aerosols produce more, but smaller cloud droplets, which makes clouds brighter and more reflective. This aerosol effect on clouds represents one of the largest uncertainties in climate prediction. Air pollution affects cloud properties in measurable ways. Polluted air contains more particles, which can suppress precipitation while increasing cloud lifetime. These changes affect the water cycle in ways that remain uncertain. Volcanic aerosols provide natural experiments in aerosol effects on climate. Large volcanic eruptions inject aerosols into the stratosphere, producing measurable cooling. These eruptions also produce spectacular sunsets as the aerosols scatter sunlight. The study of volcanic effects helps understand human-caused aerosol effects. Cloud processing of aerosols occurs within clouds. Aerosols that serve as condensation nuclei become incorporated into cloud droplets. Chemical reactions within droplets can transform the aerosols. When precipitation falls, it removes the aerosols from the atmosphere. Acid rain results from chemical transformations of pollutants within clouds. Sulfur dioxide and nitrogen oxides from pollution react with water to form acids. The resulting precipitation is more acidic than natural rain, affecting ecosystems and structures. Air quality forecasting combines understanding of emissions, atmospheric chemistry, and weather patterns. Pollutants accumulate when winds are light and atmospheric stability prevents dispersion. Changes in weather patterns determine when poor air quality will develop and when it will clear. The health effects of air pollution include respiratory and cardiovascular problems that affect millions of people. Fine particles penetrate deep into lungs, causing problems that range from coughing to premature death. Understanding the relationship between pollution and health helps inform policies that protect public health. The future of air quality involves balancing emissions from increasing population and economic activity against controls that improve air quality. The relationship between air quality and climate adds complexity to decisions about emissions. Understanding these relationships helps create policies that address both air quality and climate. Weather forecasting combines observation, analysis, and prediction in a continuous process. The observations come from thousands of stations worldwide, from instruments in the atmosphere and from satellites. The analysis combines these observations into a picture of current conditions. The prediction extends this picture forward in time using computer models and human interpretation. Surface observations provide the foundation of weather forecasting. Automated stations measure temperature, pressure, humidity, wind, and precipitation. These measurements are collected globally, providing the network of conditions that analysis begins with. Upper air observations come from weather balloons launched twice daily from stations worldwide. The balloon-borne instruments measure temperature, humidity, and wind through the atmosphere. These profiles reveal the three-dimensional structure that surface observations cannot capture. Radar observations detect precipitation within clouds, revealing storm structure and intensity. Doppler radar adds information about wind patterns within storms. The continuous scanning of radar provides the detailed picture of precipitation that enables severe weather warnings. Satellite observations provide global coverage, particularly over oceans where few surface observations exist. The various satellite channels reveal information about temperature, moisture, and cloud properties. These observations fill gaps in coverage that would otherwise limit forecast accuracy. Numerical weather prediction uses computer models to simulate atmospheric behavior. These models divide the atmosphere into a three-dimensional grid and solve the equations of atmospheric physics at each grid point. The calculations require enormous computing resources and produce forecasts that have improved dramatically over decades. Ensemble forecasting runs multiple model versions to estimate forecast uncertainty. Small differences in initial conditions or model physics grow over time, producing different forecasts. The spread among ensemble members indicates forecast confidence. Human forecasters interpret model output using knowledge of local conditions and atmospheric processes. The combination of human expertise and model guidance produces the best forecasts. Forecasters also communicate forecasts to users in ways that convey uncertainty and support decision-making. The prediction of specific weather events remains challenging. Small errors in initial conditions or model physics can produce large errors in forecasts. The chaotic nature of the atmosphere limits prediction skill beyond about 2 weeks. Within this limit, forecasts improve as models and observations improve. Precipitation types vary with temperature profiles in ways that determine impacts on society. Rain, snow, sleet, freezing rain, and hail each form under different conditions and create different hazards. Understanding these differences helps communities prepare for winter weather impacts. Rain forms when temperatures remain above freezing from cloud to ground. The simplest precipitation type. Raindrops form when cloud droplets grow large enough to fall. The size of raindrops depends on the conditions in the cloud where they formed. Light rain comes from smaller drops. Heavy rain comes from larger drops. Snow forms when temperatures remain below freezing throughout the cloud and below. Ice crystals grow as water vapor sublimes onto them, building the elaborate snowflake patterns. The temperature and humidity profiles determine whether crystals remain separate or clumped together. Sleet forms when snow melts as it falls through a layer of warm air and then refreezes before reaching the ground. The refreezing produces small ice pellets that bounce when they hit surfaces. Sleet makes roads slippery, though less hazardous than freezing rain. Freezing rain is the most hazardous winter precipitation type. Snow melts in warm air, then falls through cold air near the surface that supercools the drops without freezing. The drops freeze on contact with surfaces, building up ice that can collapse structures and make travel impossible. Hail forms in thunderstorms with strong updrafts that carry raindrops to great heights where they freeze. The hailstones grow as water freezes onto them, sometimes producing concentric layers. Large hail can damage crops, vehicles, and buildings. Graupel forms when ice crystals collect supercooled droplets that freeze onto them, producing soft, rime-coated particles. These differ from hail in their formation process and typically are smaller. Graupel is common in winter storms. The prediction of precipitation type requires detailed temperature profile information. Small changes in the profile can shift precipitation type, producing large differences in impacts. Forecasting precipitation type remains challenging, particularly during transitions. Impacts from different precipitation types require different responses. Rain requires drainage. Snow requires plowing. Freezing rain requires treatment and closures. Understanding which type is coming enables appropriate preparation. As our story slowly comes to an end, allow the final thoughts to fade. Gently into the quiet of the night, the rain and the calm ideas and the peaceful moments we've explored can settle softly in the background, like distant echoes of a quiet evening. There is no need to think about anything now. Your body can continue to relax, breathing slow and steady. If you are still awake, simply remain here a little longer and enjoy the calm atmosphere. And if sleep has already started to find you, let it arrive naturally and without effort. Thank you for spending this quiet moment here on Cozy Sleep Time. If you enjoy these calm stories and gentle explorations, you can return anytime for another peaceful journey into rest. For now, let the night grow quieter and quieter and quieter, and allow yourself to drift deeper into sleep. Good night.